So for this question, we'll be printing all the prime numbers that are less than or equal to some number or limit. Okay. So let us see the conventional way of doing it first. So if you look at the code here, say our limit, that is the number till which we have to find the prime number, is 56. This can be any number which you can change. So the algorithm that we'll be using is, first we need to define this limit, then we need to define the edge cases. So as you can see here, what we've done is, if the limit is less than 2, that is if the number is any negative number or 0 or 1, in such a case we don't have any prime numbers to print, hence we print none. So this is the boundary condition. Otherwise we can carry on with our algorithm. So we find that in the first case we print the number 2. Since 2 is a prime number, we have to include it. Why we are printing 2 at first, I'll explain it later. After that, if we look at a real code here, so what we are doing is, we are iterating using a for loop, starting with number 3 till our limit. The plus 1 at the end is because the value here, limit plus 1, is not considered in the range function for the for loop in Python. So we are basically iterating from the number 3 till our limit number, and for each such number we are checking if the number is even at first. So if it's an even number, then it is obviously not a prime number, hence in such a case we can go to the next step so as to improve the time complexity. So given that the number is not even, the next step that we need to do is we need to check for its factors, whether it has any factors. If it has factors, then we know that it's not a prime number. So for that, we are running another for loop where we are checking for the factors starting from the number 2 till the half of the number that we are checking the factors for. The reason we are not doing for n in range 2 to the entire num is because for any number, we know that the factors will be present till num by 2. For example, if you have 10, at max 5 can divide 10. After 5, 6, 7, 8, 9, they can never divide 10. So in that way, we are reducing some iterations so that we can improve the time complexity. Okay. So for each such number, we need to check whether the number that we are checking the factors is divisible by the by the variable n, whose value is from 2 to the other numbers. So we see that if it is divisible, then we break from the loop. So in that case, we know that the number is not a prime number, hence we break from the loop. So here you will find this syntax that after for we are using an else construct. We know that there is no if construct for this else. The reason being that Python does allow you to use else constructs with loops, and the syntax for that is, if in a for loop the break statement doesn't get executed, then in such a case the else block gets executed. So if you see properly, for the numbers where break is executed, those numbers are not prime because those numbers are divisible by n, hence we are breaking from the loop. So in such a case, we won't print that number. But say if we are checking for a number which is prime and we are iterating from 2 till half of the number and none of them satisfy this condition, in such a case the break statement doesn't get executed. So after this for block is executed, the else block is executed where the number is printed. In that way, the prime number is printed. So now if we run this code, you will see that all the prime numbers till 56 is printed. So we can change this to any value we want. Okay, so this is the traditional way of doing it, which actually has a bad time complexity. So let's move on to a far more efficient way of doing it, which is known as the sieve of Eratosthenes. Okay, so this article is from Geeks for Geeks, and the basic principle here is that, say we take the limit number as n equal to 50. So the algorithm here is, we have to take a binary array, that is a list in Python, that is a list where what we do is we create an array or a list which is equal to the length of the number n. So you can take a binary array where the indexes will represent the numbers till 50, and what the algorithm states here is that, so if we take a list with say for example n equal to 50, so we have 50 numbers here, we start from 2. So what needs to be done is we start with number 2, and we mark out all the numbers that are multiples of 2, provided the number has to be greater than or equal to the square of 2. So if we do that, we see that we are marking all these numbers, since these are all multiples of 2 and all are greater than 2 square. So after we are done with 2, then we move on to 3 and go through the same procedure. So after we are done with 3, we see that all of the multiples of 3 which are greater than 3 square, greater than equal to 3 square, have been marked. After that we follow the same process for 5, and we go on till uh, the boundary condition for this algorithm is that for every number that we are checking, we know that the numbers that we will be marking out has to be at least greater than equal to the square of the number we are taking into account. So say here in this case, since the greatest number here is 50, so we see that at max we can take till 7, since 7 square is 49. If we take 8 in the iteration, we know 8 square is 64, so there is no chance of marking any number, since the maximum number here is 50. So this is the algorithm for the sieve of Eratosthenes. So what this does is it reduces the time complexity to let me see, yeah, the time complexity gets reduced to O of n into log of log n. So if we check the code, what we're doing here is, say we take n equal to 56 like before. So first we need to check the boundary condition. So if n is less than 2, we print none, since there are no prime numbers to print. After that, first we need to declare a binary array where the length of the array is equal to the number n, and for every element in the array we will initially print it as true. So when we are finally printing the prime numbers, only the elements that have true as value, we will be printing the indexes of those elements in the array. So the reason we are taking it as n plus 1 is because since the array starts from 0, and we know that we are not considering 0 and 1 in the prime number list. So basically this Boolean array, the first two elements will not be considered by us. So we start with 2. So as discussed before, what we are doing is we will only take those numbers into consideration whose square is uh, less than or equal to the maximum size of the array. Because if the square of the number we are taking into account exceeds the maximum limit that is given here, then we cannot apply the algorithm. So after this condition is satisfied, next what we check is whether the element of the array is true. Because if it is false, we know that the number is already not prime, so we leave that. But if it is true, there is still a possibility that it might be a composite number. So following the algorithm, what we do next is, so for the number we took in the iteration, we will have to start marking out all the multiples of this number I, starting from I square, since the limit has to be, any number that we are marking out has to be greater than or equal to I square. So we are starting out at I square, we are going till the limit. Remember, we are doing n plus 1 because the array starts from 0 and we have to take 56 into account as well. And we are moving the for loop forward by count of I, because we will only be marking out the multiples, right? So for example, if I is 5, so this loop will get this I will get incremented by 5 every time, since we know that the multiples are at a gap of 5, just like that. So for all those multiples, the element for that particular index, we mark it as false, and after we are done, we increment I to 3, and again we are incrementing it like that. So for each time we are incrementing it, we again have to check whether the number whether the value at that index is true or not. If it is true, then we follow the same procedure, and if it is false, we don't do anything. So after this algorithm is done, Now finally we have to print the prime numbers. So for that what we do is this array that we have modified so much, so we will only print the indexes of those elements whose value is true, because we know that if it is false they are composite number. So that is what it is done by. So this is the algorithm for sieve of Eratosthenes. So if we run this, we find that all the prime numbers are given.